This video will introduce basic pulse sequences, including introducing the concept of pulse sequence parameters, TR and TE, and how those parameters can be manipulated to get T1 weighted and T2 weighted images. Then we'll illustrate those concepts by showing you how we get MRCP images. I'll be honest, it's tough to do justice to this topic in a short video, so if you have no background and this gets a little confusing, don't worry, just keep watching and understand the key principles toward the end of this video, namely that short TRs emphasize T1 effect and long TEs emphasize T2 effect.
Remember, pulse sequences are essentially precisely timed RF pulses or radio frequency pulses and gradients designed to generate MR signal that can be detected and turned into an image. The parameters of the pulse sequence are what will determine the tissue contrast. For example, whether they're more T1 or T2 weighted. A gradient echo pulse sequence is one of the simplest pulse sequences. A gradient echo pulse sequence starts with a single RF pulse. For example, this is a 90-degree RF pulse, but it can be lower. Magnetic field gradients are then applied, and we don't have time to go into details about gradients, but essentially gradients result in a varying magnetic field in space in a particular direction. Essentially a gradient in magnetic field in a direction, that's why they're called gradients. So you can have X gradients and Y gradients that vary in the X and Y planes respectively, for example. If the magnetic field strength is different in different positions, for example in the X-axis, then we know from our Larmor equation earlier that hydrogen atoms are going to spin at different frequencies in different locations. So with that, gradients allow us to make the RF pulses selective to a particular slice of tissue. It allows us to collect data from a very specific area and spatially localize the MRI signal, i.e. know where the MRI signal is coming from. This is beyond the scope of this talk, so we're not going to talk about gradients very much more, and we're really not going to include them in our diagrams and muddle up the picture. So we have this RF pulse, gradients do their thing, and then sometime later we have this echo, and this is a gradient echo. This is signal that we can sample. And then we do it again a little bit later with another RF pulse and then another echo down the road here. Okay, so now we have enough information here to define two key pulse sequence parameters, TE or time to echo and TR or time to repetition that are both measured in milliseconds. The TE is the echo time or time to echo, which is defined as the time in milliseconds from the center of the RF pulse to the center of the echo. The TR is the repetition time or time to repetition, also measured in milliseconds, defined as the length of time between corresponding consecutive points on repeating series. More simply put, from RF pulse to RF pulse. These parameters are important and are what determines tissue contrast. This is a very important point. You can have a gradient echo sequence that is more T1 weighted, T2 weighted, or somewhere in between. The type of pulse sequence doesn't determine the tissue contrast. The pulse sequence parameters, i.e. TE and TR, predominantly do. In a spin echo pulse sequence, there are two RF pulses at the beginning. We have a 90-degree RF pulse here followed by an 180-degree RF pulse. Technically speaking, a spin echo can start with any two RF pulses, but Most commonly, we use a 90-degree RF pulse followed by a 180-degree RF pulse. And that's how we identify that this is a spin echo sequence. So the 90-degree RF pulse here tips the spins into the transverse plane and causes the nuclei to precess in sync in the XY plane, as we've mentioned multiple times. Over time, after this 90-degree RF pulse, there's going to be some longitudinal relaxation back towards the z-axis and transverse relaxation or T2 relaxation. Also remember that there is transverse decay due to magnetic field inhomogeneities, what we introduced when we talked about T2 star. If certain nuclei experience a lower magnetic field, they're going to precess slower than the other protons, get out of phase, which is going to result in a loss of signal in the transverse plane. So, after all of those types of relaxation are occurring in the interim, we then apply a 180-degree pulse, which is also called a rephasing or refocusing pulse. The 180-degree pulse is halfway between the 90-degree pulse here and the echo, which is also known as the TE. So the 180-degree pulse happens at 1/2 of TE. The purpose of this 180-degree pulse is to bring the nuclei that precess out of phase due to magnetic field inhomogeneities back into phase. We then have our spin echo here, and the signal that we get here is not as sensitive to signal loss from magnetic field inhomogeneities as the gradient echo that we showed earlier. Again, we have the TE and TR, and these are the parameters that determine the tissue contrast. The way that this rephasing pulse is often explained is through an example of race cars in a race or runners. If we have one car traveling faster, which will be 1, than the other, which is 2, the car that travels faster, like a hydrogen molecule that experiences a stronger magnetic field and therefore has a higher frequency, will get out of phase with the slower proton or slower car. So if we let that play out for some period of time after a 90-degree RF pulse or the start of a race, they start to get out of phase due to the differences in frequencies or speeds if we're talking about cars. If we turn those cars around like that to face the start line again after a certain amount of time, and then we wait the exact same amount of time, the two cars will be back in phase at the start line. That is equivalent to the 180-degree pulse turning the spins backwards, and after the exact same amount of time, the spins will be back in phase. So the takeaway point here is that the spin echo sequences use this refocusing or rephasing pulse to reduce magnetic field inhomogeneities through this mechanism, and you can recognize a spin echo by having two RF pulses, usually a 90 and 180-degree pulse at the start. We mentioned earlier that the type of pulse sequence itself doesn't determine the tissue contrast. The type of contrast is mainly determined by the TE, time to echo, and TR, time to repetition. If you remember two things from all of this, remember this. 1, shorter TRs will emphasize T1 effect, and longer TEs will emphasize the T2 effect. So why is that? Let's start with why short TRs or short time to repetitions emphasize T1 effect. Well, if we had shorter TRs, think about what happens when we repeat the pulse sequences. When we repeat the pulse sequences with a short TR, we do it so quickly that we don't let the magnetization completely recover into the z-axis before we start the next sequence. So different tissues have big differences in T1 signals, and that determines tissue contrast. So to illustrate that here, we've simplified our diagram into just showing the z-axis, and in blue we have water molecules, and in yellow we have fat molecules. If we apply a 90-degree RF pulse, the entire net magnetization vector is in the xy plane, and therefore there is nothing in the z-axis. After a very short period of T1 relaxation, these begin to relax in the longitudinal plane. The fat molecules, or hydrogen molecules in fat, have a much shorter T1 relaxation time, and so they relax towards the z-axis a lot quicker, and after a very short period of time have a bigger net magnetization vector in the z-axis. If we then applied an RF pulse at this time, the amount of signal that we would detect in water would be very low, and the amount of signal that we detected in fat would be very high, and that would be based on the differences in T1 relaxation differences between those tissues. So a shorter TI emphasizes that difference in the T1 relaxation effect. To illustrate that more, if we had waited even longer and had a long TR, we would have let the water and fat molecules completely relax into the z-axis, and then if we apply an RF pulse, there's no difference between the tissues, and so we've now completely gotten rid of any differences in T1 relaxation. So remember one thing here, again, short TRs emphasize the T1 effect for the reasons that we just mentioned. Also remember that longer TEs emphasize T2 effect. If the TE is extremely short, we're listening to the echo, we're detecting the echo right away, and we're not allowing much T2 decay to occur. If the TE is relatively long, we're allowing more T2 decay to occur before listening, and tissues will have different signals based on their T2 effects. If that doesn't make any sense, just remember what's on the screen. Short TR emphasizes T1, and long TE emphasizes the T2 effect, and you'll already be most of the way there. If you know those two things, then it makes sense that a T1 weighted sequence, or if you want to make a sequence that's T1 weighted, you're going to use short TRs to emphasize the T1 effect, as we mentioned, and you're going to use short TEs to get rid of or minimize any T2 effect. We want the images to be predominantly T1 weighted. T2 weighted images should use a long TR in order to minimize the T1 effect, and a long TE to maximize the T2 effect. Proton density, or PD, sequences aren't really used that much in routine body imaging, but they use a long TR to minimize T1 effect and a short TE to minimize T2 effect. And if you minimize both the T1 and T2 effect, you're just left with the density of protons. That's why it's called proton density. But again, we don't really use that much in routine body imaging. So let's apply these concepts to something clinically relevant. This is an MRCP, or magnetic resonance cholangiopancreatography image. It's a technique used to image the biliary and pancreatic ducts and help us look for things like stones, strictures, tumors, etc. We're really trying to get a good look at the ducts, and this is the CBD here, these are the intrahepatic ducts, and this is the pancreatic duct here. This is an example of a thick slab MRCP image, and we'll talk about how we acquire these in a little bit. But essentially, these are just very, very heavily T2 weighted images. Remember, water is very bright on T2 weighted images because water has a long T2 relaxation time. So if we emphasize T2 effects to a very, very high degree, we're going to get something like this, where signal is lost everywhere else, and only the water, or things like water, are maintaining their signal. MRCPs, therefore, use very long TEs. Remember, long TEs emphasize the T2 effect. So they use very long TEs to produce these images. Most other things lose the signal, and the water and the bile ducts and the pancreatic duct maintain their signal, and we get great images.